Calculus, video 72, even and odd functions with the fundamental theorem of calculus. Alright, so a little bit of review. Even functions. Some examples of even functions are simply like y equals x squared, y equals 4 minus x squared, y equals x to the fourth minus 3x squared. Those are all polynomials. And what you'll notice is if your polynomial only contains even exponents, and constants have even exponents because constants like 4 could be thought of as like 4x to the 0 power, x to the 0 being 1. Okay? So polynomials like this that have only even powers are even functions. Things like y equals the cosine of x, that's an even function. Y equals secant of x, that's an even function. So those are examples of even functions that we have. And what it means to be an even function are these functions are symmetric about the y-axis. Symmetric about the y-axis. For example, if you were to take a look at a graph of, say, 4 minus x squared, 4 minus x squared looks something like this. And despite my poor drawing there, that should be a symmetric about the y-axis. Okay. Odd functions, similarly, y equals x cubed is kind of the classic odd function. Y equals x to the fifth plus 2x cubed plus 4x. All have odd exponents, is an odd function. Y equals sine of x, that's an odd function. Y equals tangent of x, that's an odd function. Odd functions, we call that symmetric about the origin. Symmetric about the origin. Let's just take the classic x cubed. X cubed looks like this. And what you can see is it's like the right part of the curve has been flipped over the x-axis and flipped over the y-axis to line up with the left part of the curve. We call that symmetric about the origin. Okay, so even and odd functions. What we want to do is use the fundamental theorem of calculus with even and odd functions, specifically when the bounds, the lower bound and the upper bound are the same value, but the lower bound is negative. So we're specifically thinking about things like this. What is the integral? So for example, what is the integral from -3 to +3 of, let's go with 16 minus x squared dx? So this 16 minus x squared, that is an even function. And the bounds here go from -3 to 3. And that part's important. We're gonna only focus on bounds that go from like -a to +a, from the same number negative to the same number positive. And what we're thinking about here is this. Take a pic. Let's just redraw this. 16 minus x squared. 16 minus x squared looks like. And maybe more like. That's close enough. Y equals 16 minus x squared. That would cross here at -4 and at +4 on the x-axis. We're gonna look at this from -3 to 3, and so -3 is about right here, and +3 is about right here, at least somewhere about there. And so what I want to think about here from -3 to 3 is that the area on the left of the y-axis in red here, and the area to the right of the y-axis, say in black right here, are the same. Let's not do that. All right, so the area to the left and the area to the right are the same. And so if you have an even function, and it is going from negative a to a on the bounds, you can do this. Instead of going from negative 3 to 3, we could go just from 0 to 3, just half of it, and then double our answer. Right? So we could say negative 3 to 3, the bounds negative 3 to 3, the integral 16 minus x squared dx is equal to twice the integral from 0 to 3, just the part in black there, but you're doubling it because it's the exact same area on the left-hand side, of 16 minus x squared dx. And you might ask, well, why do I want to do that? Well, sometimes when you have complicated integrals, plugging in 0 into one of the bounds makes life just a little bit easier because it's a lot of times easy to plug in 0. That the answer is either 0 or something fairly simple. So sometimes this just makes our life easier. I'd rather plug in 0 as my f of a than I would negative 3. So maybe I save myself 20 seconds, but sometimes saving 20 seconds feels pretty good. So if I did this integration here, I would get 2 times 16x minus 1/3 x cubed evaluated from 0 to 3. That's 2 times. Plugging in the 3, I get 16 times 3 minus 1/3 3 cubed. And this is the good part. Minus plugging in 0, 16 times 0 is 0, 1/3 0 cubed, 0. Save a little bit of time. That's twice. 16 times 3, 48, minus 3 cubed, 27 divided by 3 is 9. 48 minus 9 is 39 times 2 is 78, I believe it is. 78. Okay, so this right here, this makes us happy, plugging in 0. So a lot of times you'll see when we go an even function, negative a to a, we'll go 0 to a and double it and make our life just a little bit easier. That works for all even functions as you're going from negative a to a. I say that as long as you're not going across a vertical asymptote. For example, that secant function up there, right? The secant of x looks like this. It is an even function. That's not very good. Let's try that again. An even function, but then you get this vertical asymptote, and you get part down here, and you get a part down here. That happens at negative pi over 2 and pi over 2. So as long as you're staying between negative pi over 2 and pi over 2 to pi over 2, then it works just fine, and you can do this. You can go, from, if you did here to here, from this negative a to this positive a, that's perfectly fine. But once you go across that vertical asymptote, now you're looking at a possibility of an infinite area. That's something we'll save for Calc 2 when we talk about infinite limits, infinite integrals. Okay, so in general, as long as we don't cross over a vertical asymptote or a place where the function is undefined, if it goes from negative a to a and it's an even function, we can do this. Even function. Let's say f of x is an even function, then the integral from negative a to a of f of x dx is equal to twice the integral from 0 to a of f of x dx. Saves a little bit of time. And that's good. We like saving time. But the next one's going to save us even more time. And that is what happens when the function is odd. All right, let's go back to the curve y equals x cubed. Y equals x cubed looks something like this. Now, let's go from, say, negative 2 to 2. Negative 2 here, positive 2 here. And we look at the area, the signed area under the curve, and we get this part here in green. And we get this other part here, say, in red. That's not red. Red. What do you notice about the two areas? They're the same area, it's just that one is negative and one is positive, and when we put them together, what's the overall area? It's 0. It's 0. So for an odd function, let's go ahead and walk through that. If I have the integral from negative 2 to 2 of x cubed dx, that would be 1/4 x to the 4th, evaluated from negative 2 to 2. If we plug in, pull out the 1/4, if we plug in 2, we get 2 to the 4th, minus negative 2 to the 4th. That would be 1/4 times 2 to the 4th, 16, minus negative 2 to the 4th, also 16, and 1/4 times 0 is 0. We get an answer of 0. But if we recognize that this is an odd function, x cubed, and the bounds go from negative 2 to 2, or any sort of negative a to a, we can just automatically put an answer of 0. And just say, hey, this is an odd function on negative a to a, therefore the answer is 0. There's 0 area under the curve. And that can be a huge time saver because we don't have to do any of that work. All right, if I solve the problem negative 2 to 2 of x cubed dx, I would say 0, because that's an odd function. And we're going from negative a to a. Done. That's it. We like that one. Right, we like that one. So in general, it looks like this. If we'll go g of x is an odd function, then the integral from negative a to a of g of x dx is equal to 0. All right, and that is using even and odd functions with the fundamental theorem of calculus.